Today, we're going to talk about rare events and how we can deal with them in Cochrane reviews. So let's see the structure of the session. We will see what rare events actually mean and how we can deal with them in Cochrane reviews. We will present all the statistical approaches which can be used for analyzing rare events, and we will emphasize on the standard meta-analytical models which are available in RevMan, but also we will present their limitations. And we will talk about very briefly about some alternative meta-analytical options that we can use instead. In the end, I'm going to give you some short take-home messages, and of course, there will be plenty of time for discussion and answering your questions. So, regarding the definition of rare events, there is no globally accepted definition of what constitutes a rare event. When a small number of events, even zero, is observed in the studies at hand, then we can say that we have a rare outcome. Most researchers suggest that when the outcome risk is below 1% or even below 0.1%, then we can say we have a rare outcome. The Cochrane Handbook mentions that even if the outcome risk is close to 10%, we might have issues. So in this case, we might also treat our data as rare. It is quite a common issue when we study important safety outcomes to have rare data. For example, if we study different types of adverse effects. And meta-analysis can be a powerful tool for synthesizing studies, which might be underpowered due to rare outcomes. So in this case, we have the ability to increase the overall statistical power. Let's see a typical example. This is a meta-analysis from a published Cochrane review. Authors investigated whether laser-assisted cataract surgery would decrease the odds of posterior capsular tears compared to standard cataract surgery. As you can see, we have overall 27 studies investigating this comparison. But the maximum number of events per arm is only 6. We have 17 double-zero studies. That means in both arms we have 0 events. So only 10 studies contributed to the summary estimate of the meta-analysis. Rare events are quite common in Cochrane reviews. In a systematic review, which included a sample of 480 Cochrane reviews, authors found that 35% of these reviews had an adverse events meta-analysis, and approximately 30% of these meta-analyses had at least one study with 0 events in one arm. The most common summary estimates used for the meta-analytic estimate was the Petos odds ratio, the Madden-Hensel odds ratio, and risk ratio, and the risk difference. In another systematic review, which included close to over 4,000 rare events meta-analysis of Cochrane reviews, authors found that 12% of these rare events meta-analysis had sufficient power to detect a relative risk reduction of 50%. And authors concluded that meta-analysis of rare events need a much larger number of studies to ensure sufficient power. So despite the issue of rare events, in terms of statistical power, we also have a huge problem if we also have a small number of studies. So the standard meta-analytical models, which are also available in RevMan, and we will review in detail in the next slides, are the fixed and random effects inverse variance methods, the Madden-Hensel method, and the Petos method. So both fixed and random effects inverse variance methods are 2-stage models. That means that we need the estimate of the intervention effect and the corresponding standard error from each study. And then all these individual estimates will be synthesized. A fixed effect meta-analysis is valid under the assumption that all effect estimates are estimating the same underlying intervention effect. On the other hand, the random effects meta-analysis, known as the Darsimonian and Laird method, assumes that the different studies are estimating different yet related intervention effects. The fundamental difference between those two methods is the assumption of the between studies variance. The extent of the between study variance is expressed using the tau square value, which is incorporated in the random effects weights. So if we go back to our previous example and apply both our fixed and random effects models, we have an estimate of 1.06 in both cases. And that is explained because tau square was estimated to be 0. If we apply the Madden-Hensel method, which is a fixed effect approach that uses a different weighting scheme that depends on which measure we're using in our meta-analysis, then we might have different results. Madden-Hensel method has no distributional assumption. The inverse variance methods assume that the within-study intervention effects are normally distributed, but the Madden-Hensel method is a non-parametric approach. So if we want to calculate the Madden-Hensel odds ratio for the meta-analysis, we will use the 2x2 table of number of events and number of non-events per hour. So we can apply Madden-Hensel method using a fixed and the random effects approach. And in this case, we have a 0.86 summary estimate if we use the fixed effect approach and 1.06 if we use the random effects approach. Keep in mind that the random effects approach, when we use the Madden-Hensel method, it's not actually a random effects meta-analysis, because what we do here to estimate the between study variance is to compare each study's result with a fixed effects Madden-Hensel summary estimate. Finally, if we apply the Peter's method, which is a fixed effects inverse variant approach and very similar to Madden-Hensel method, to combine odds ratios alone, we again need to use the 2x2 table of events and non-events per hour. Again, we have no distributional assumption. And if we apply this, we have an estimate of 0.83. So in total, we applied 5 different models to estimate our summary, to calculate our summary estimate, and we have 5 different estimates. As you can see, the fixed effect inverse variance, the random effects inverse variance, and the random effects Madden-Hensel methods give the exact same summary estimate. On the other hand, the fixed effect Madden-Hensel and the Peter method give a different summary estimate. So my question to you right now would be, if you were one of the authors of this review and you would like to analyze this data, which method would you choose? So we have a poll for you. So the possible answers are none, fixed effect inverse variance, random effects inverse variance, fixed effect Madden-Hensel, random effects Madden-Hensel, and Peter. The correct answer is only one, but this is quite tricky. So I'll give you a couple of minutes to answer to this poll. Well, 45% of you answered none of these methods, but I would say that Peter method might be a good choice here to analyze data, and we will see why in the next slides. So these are the results. Okay. Limitations of standard meta-analytical models when we analyze rare events are quite a few. First of all, the inverse variance methods are not appropriate at all for meta-analyzing rare events. And that is because we use a normal approximation of the true binomial likelihood, the large sample approximation, which does not work well when event rates are low. The within studies, normality assumption does not hold in this case. plus the estimation of the variance of random effects, that means heterogeneity may be biased, which may lead to spuriously narrow confidence intervals. In simulation studies, on the other hand, P2 method gave the least biased summary estimate and best confidence interval coverage, as long as there was no substantial imbalance between intervention and control group sizes, and treatment effects were not exceptionally large. But also P2 can be problematic, especially when zero events occur in all arms of all studies. In a systematic review by Sarma and colleagues, authors concluded that this method was not robust for meta-analysis of rare events using data from antidepressant trials. In any other circumstances, such as when we have event risks above 1%, we have very large effects, and meta-analysis includes studies that are substantially balanced, the Madden-Hensel fixed effect method should be preferred. But also, we have to keep in mind that Madden-Hensel can be problematic when zero events exist for the same arm across the studies. An additional limitation that applies to all of the standard meta-analytical models is that studies with zero events are excluded, since calculation of treatment effects and their corresponding errors becomes impossible. We need to divide by zero. Let me remind you the formula for the standard error of the log-odds ratios. As you can see, if we have zero events in at least one of the two arms of the study, then we cannot calculate standard errors. By default, Revman does a continuity correction. That means that it adds a value of 0.5 to studies with zero events in only one arm. So some possible remedies which have been proposed to improve the performance of these standard meta-analytical models is the continuity corrections. That means that we can add a value to the zero event studies so we can incorporate them in the meta-analysis, or we can use risk differences instead of risk ratios or odds ratios. So let's see how continuity correction performs. So we have three different scenarios. The first scenario, which is presented in the second column, is that we include studies with non-zero events in both arms. In our previous example, we had only 3 studies which had non-zero events in both arms. The second scenario is to include studies which have 0 events in only one arm. That means that we have 10 studies. And the third scenario is to finally include all studies. That means that we can include all studies with 0 events in both arms. The first approach is not recommended at all because we have an underpowered analysis. So if we start excluding studies, even though they might have 0 events in only one arm, that means that we make things even worse. So this approach is a big no. The third column gives us the results that we saw in previous slides. And the final column gives the results if we apply the 0.5 continuity correction. So we now have all of the 27 studies included in our meta-analysis. As you can see, the two last columns give some results which are not very different, but simulation studies report excessively biased estimates after applying a 0.5 continuity correction, especially in fixed and random effects models. There's also another method in which we can use a non-fixed correction. That means that the continuity correction is not just 0.5, but it depends on the different treatment arms of each study, and it is inversely related to the size of the treatment arm. This method has a better performance than the 0.5 continuity correction, but it has been criticized as well. And the second approach is to use risk differences instead of odds ratios. And as you can see, we were able to calculate risk differences using 27 studies this time for 4 out of 5 methods. But in the presence of rare events, risk differences have very poor statistical properties. That means that they have very wide confidence intervals and low power, so they are not appropriate for meta-analysis. So the literature has suggested that instead of relying on standard meta-analytical models, we might need to use alternative meta-analytical models. And as you can see, we have a huge variety of different meta-analytical models. We will not go through all of this, but I will show you what simulation studies have shown about the performance of these models. So simple logistic regression performs similarly with the Madden-Hessel method with no continued correction. If we apply Bayesian meta-analysis model for rare events, then we need to be very careful with the choice of prior distributions because non-informative priors may dominate results. We might also use a beta binomial model with correlated responses, and this model can include studies with 0 events in one or both arms without any continued correction. This model has been shown to perform really well in various settings when studies are balanced. We can also use arc-sign differences, which is an effect measure that tackles all the problems associated with rare events meta-analysis, but usually arc-sign differences are very difficult to interpret in clinical terms. And finally, simulation studies show that heterogeneity plays a significant role in the estimation of our summary of summary estimates, but Cochrane Handbook suggests that heterogeneity should not be a priority. We should focus on finding the most appropriate model for a final estimate. So my take-home messages to you would be that in case you have rare events in your analysis, meta-analysis might be the only way to investigate relevant outcomes. The inverse variance models should be avoided because the assumption of within studies normality does not hold, and we have biased estimates. We should not use continuity corrections or calculate risk differences instead of odds ratios and risk ratios. P2 methods and a fixed effect Madden-Hessel method without continuity correction seem to work well under very certain circumstances. We have also a variety of alternative meta-analytical models, and these models can incorporate studies with 0 events in one or both arms without any continuity correction. But regardless of the statistical model that we will choose, we need to be careful because estimates, meta-analytical estimates, will be inevitably imprecise. Results are very sensitive to the choice of methods that we're going to use to analyze our data. So a solution would be to do various sensitivity analysis using a variety of predefined methods. And we should also report the absolute event rates instead of our risk ratios or odds ratios in order to have a clear picture of the extent of the problem in our data. When different methods lead to results with different clinical implications, if we apply different meta-analytical models, then results should be interpreted with caution. So in case we have different results, then this can be considered as hypothesis generating. And if you have rare events in your analysis, then I would suggest to talk with a statistician because things are more complex than they look. So finally, I would like to thank Dr. Anna Haimani and Dr. Theodorou Sevrenoglou for the Cochrane Colloquium workshop on rare events meta-analysis, which was really informative. These are the references, and we can have some time right now for some general discussion and answering your questions.